Так, можно начинать, да, там работает.
Вот здесь и вот здесь.
Так, мы начинаем, если что. Okay, so characteristic classes. So the goal is to present the following construction. If I have a principal G bundle, I have so I have the following data: principal G bundle, some map, and a representation. So, as I said, P is principal G bundle. So representation, so rho is a representation, meaning that it's from G, and it is complex representation. It is homomorphism from G to some GLN C, for some n. What?
Это ровный звук.
Yes. This is P. Yes, this is big P. This is rho. Then, and F here is a map from, well, should say GLN C, so n by n complex matrices, basically, to C, such that it is invariant with respect to conjugation. So f of ABA inverse is the same as FA for any A from GLN C, GLN small, and B should be invertible. So GLN capital C. B. Okay. So, right. So so I have this data which I described here, and by this data, my goal is to construct some form, differential form, that will be denoted usually like this. So this, well, this is differential form, but it actually will give me an element in the RAM cohomology. Of X. So P is principal G bundle on X. And so this is the X. And this element will be called characteristic class because, sorry, this should be P here, right? So F rho
Класс чего? Просто мы вроде...
Ну, как их можно, я не знаю, класс обычно. Наверное, это имеется в виду класс эквивалентности.
Ну, а мы что-то факторизовали?
Ну, когда вы, не, ну как, вы получаете форму, а когда вы рассматриваете когомологию, вы,
все, да, окей. Понятно.
То есть в когомологиях живут классы. Yes, and characteristic means that actually it doesn't depend on P, but depends rather on isomorphism class of P. And so for this this element in here is the same for isomorphic principal bundles. Okay, so how do I want to do this? Well, first okay, so I will do it using connection, using some connection. So suppose that I have a P. So first I will choose connection, principal connection on P, and then construct something and then prove that this actually does not depend on the connection. Okay, so so let omega be, so omega is connection one form in the sense that we just discussed. So so principal connection. So it means that it lives inside gamma of T star P tensor P times G. Lie algebra G. What I want from this, so claim is that omega defines an element so it defines a section of the following actually vector bundle over X. So it's well, I have I have connection one form. Out of it, I actually need curvature of this connection, which is, as we learned, is just omega of commutator of vector fields. This is actually, this gives me two form, right? This will leave, so I need to plug in stuff in here, right? This will give me something like lambda 2 of T star P times tensor P times G. So this is curvature, two form. Well, maybe I need to put minus in here, but that will not really matter for us at this point. So I would like to see that actually not omega, but this curvature to form defines an element where. So it's two form on X with values in this, so in the following, so P times G, but okay, this is bundle over X, so I would like this to be bundle over X, more of a vector bundle, so I write add in here. So G itself is a representation of a Lie group G, right? Corresponding homomorphism is this add, right? And I construct associated vector bundle, and this associated vector bundle will be over X, right? And well, this is now vector bundle over X, and I take my curvature and would like to obtain an element in here. How do I do this? Right. So I just would like to prove that so I would like to see the following: omega of so my form will actually, so I would like to check the following. So I take omega of the commutator of VH WH. So these are omega and W vector fields on X. And these are horizontal lifts of these vector fields. I would let me compute this at point P. Well, but shifted, well, acted on by right action by some element G. So I would like to see that this equals to, so I just compute omega of VH WH at point P. So this gives me an element of Lie algebra, and then I apply add G to it. So if I prove this, then indeed this defines an element in here. How? Okay, let me denote this element.
Это представление, но на P еще есть как бы структура Ли.
На V, на каком V? Ну, есть. Она есть, мы даже не знаем, что такое структура алгебры Ли, но как бы нам здесь не понадобится. Но это правда, она есть, да.
Ну, она в целом и зашита, что представление есть такое соединенное.
Да, совершенно верно. Да.
И только так и используется.
Ну, видимо, да. Okay, so now, yes, so how do I define, so if I have my omega, then I define element F, as I promised, right, should lead, well, so my omega, this to form, defines an element F, so which is section of lambda 2 T star X tensor P at G. So okay, it eats two vector fields, right? And at some point X, right, it should give me an element in here, right? So I define this element as follows. An element in here is an equivalence class of pairs from here. So it's equivalent class with the following representative. So I take some point P, doesn't really matter, so P is, doesn't really matter which P as long as it is in fiber of X. And then omega of commutator of VH WH at point P. So this is an element in G, this is an element in P. I take this pair and consider its equivalence class. This gives me an element in here. Okay? And so I define it like this, and if I check this, then this is actually well defined. Right? Well, just because if I take any other P from the fiber, right, then this it will be shifted by some G, right? It will differ from the old one by G, right? And this will mean This will be just this will just mean that it is the same. This at p dot g is the same as I am applying at g here. But since the but then equivalence condition says that the corresponding pairs are the same. Does that make sense? Okay, if we need to do something more details.
Просто в чем суть, то что как бы...
Утверждение в том, что вот это не зависит, что это действительно определение.
Ну,
что не зависит.
Следует из вот
Это следует отсюда. Да. Теперь давайте действительно проверим вот это. Okay, so let me write this down. So omega of VH WH of P dot G. Well, just from the definition of pullback, alpha G star omega of alpha G lower star, it is push forward of vector fields, which I can it's really well defined. Everywhere I can take inverses just because this is diffio. Of V H, well, of the commutator at point, how many? So I need to close one more. At which point? At point P. This is just from definition of pullback. Okay. This equals to, right. So the thing is that commutator, push forward respects commutator, right? So I can write this down as follows. Alpha G star of omega of commutator of alpha G lower star inverse VH, alpha G lower star inverse WH at P. Now, well, I think I don't need parentheses here, right? So this is really pullback of this thing. So this comes together. And then I take this form evaluated at this thing. So I take this form evaluated at this thing at point P. Right, and now I'm using the fact that omega is principal connection. So, so I have, well, this and also the fact that actually my VH and WH, so alpha G star, so since my connection is principal, right, and H is really related to the choice of connection, so it's horizontal, right? These vector fields, they are invariant with respect to push forwards, actually. Well, you can really check this. You can check, but this is very natural, right? Your connection is principal, so therefore horizontal lifts behave well with respect to the action of your G. So that's what it is. So what I want to say is that alpha G inverse VH is just VH, and the same for WH. So do you want me to say something more about this, or are fine with that. So no surprises. You just take the definition of horizontal lift. In this definition, you will have pi inverse, right? And actually, your pi restricted to your horizontal d pi inverse. I mean, d pi restricted to your horizontal subbundle, right? And d pi at one point is the same as d pi at the other point, composed with alpha g. And so that's why this follows. Okay. So now, yes. So this is just VHWH, and you get a joint out of here. So what we have.
Если вот это определено только
Сейчас, если это f определено, ну дальше мы с ним будем работать.
Вот такое, как это назвать? Как это называется?
Нет, ну некоторые вот это называют curvature to form. Ну вот это. Ну, просто это разные, как бы, ну, то есть можно по-разному, можно брать k, брать там, просто там, ну, в зависимости от того, что там разным людям надо, они как бы определяют, в принципе, как разные объекты, но это все одно и то же, если подумать хорошенько. Вот.
Ну, это форма кривизны, и это...
Да. Вот. Okay, so now we have that this is actually omega. Well, we have this, right? Just using this just replaced with VHWH, and alpha G star is just the same as taking it because we have principal connection. And so equals right-hand side. Let me just write it like this. Right-hand side of this one. And so indeed we have now, we can understand the curvatures form living in here. Very well. So now what do I do with it? I take, all right, so I have my rho that I just erased. So this is homomorphism from G to GLNC. Да.
Мы сейчас идем к тому, чтобы доказать, что характеристический класс...
Не, ну у нас пока нету такого пока, что мы его даже не построили. То есть мы пока что хотим использовать этот f, чтобы построить то, что мы назовем характеристическим классом. То есть пока что мы как бы некую конструкцию развиваем. Вот. А потом мы про нее что-нибудь докажем. Okay, so now we have this rho, and well, I can take a differential of this, and I will have representation of G, Lie algebra G. So this is homomorphism of Lie algebras, but we will have just this linear map. Maybe at some point I overlooked something and we will need Lie bracket, but maybe not. If we'll need, it's not so hard to introduce. Okay, and so then, so because basically this is the Lie bracket, right? Then what the, yes, so I have d rho, and I would like to now consider another representation, which I will denote as at rho. So this is a representation from G to GLN of C. So it takes elements of a group to inversible transformation of n by n matrices. And this is really an analog of adjoint representation, like after you mapped your G to GLNC, right? So you have adjoint representation here, and well, therefore it transfers to some kind of adjoint representation on here. So, right, how does it work? It just takes an element G and maps it to the following transformation. A, right, an element in here, goes to row of G, A, row of G inverse. Okay? So this is this. If rho is a representation, this is also a representation. Okay. So then we define the following element, which I denote by F with index rho. So this guy will belong to, it will be a section, so it's two form, again, on X, but with values in where? It is in with values in P times, okay, let me denote this thing by, okay, even this, by Mn. So these are n by n matrices with complex entries. So times Mn over this action, add row. So so how do I define it? I just define it by values. So I take two vector fields, V and W, so they will be plugged into this component. And then at X, I should get an element in here. An element in here is again a class with some representative. And this representative should be a pair of two elements. So a point in here, again, doesn't really matter which point as long as it is in the fiber of X. And the second component is just d rho applied to omega of VH WH at point P. So I take this at point P, right, and then apply d rho to it. So this is an element of Lie algebra. D rho makes an element of Mn out of it, which is exactly what should stay in this component. So this is my F rho. So I kind of take my F, and instead of G, I need Mn there. And so this is construction that makes it. Very well. Now I would like to right. Yeah, again, so you need to check that it is well defined using all these our constructions, but basically it just follows from the fact, so this is well defined. Let me just since we need to compare how d rho commutes with at G. So this is the same as at rho, this guy. So it commutes in the sense that on the left, if I go this goes through, I get not at G but rather at rho of G. 0. And this makes it really well defined, because this is an action in here. Okay, now well, this is, I don't know, it's an exercise going through definitions and computing differentials, and not very hard to see. Maybe one line. So now I need this construction. So suppose that I have some vector bundle over X. This will be actually this vector bundle, but just to simplify my life, let me just take any vector bundle, E vector bundle over X. And suppose that I have two forms with values in E. So I have eta 1 is differential form, so it's a section of lambda k t star, so k, a degree k form, tensor E. And eta 2 is the same kind of object, but maybe of different degree, L. I would like to see what does it mean to take wedge of them. So I would like to see, I would like to construct what is this. So this thing will be section, so this will be k plus L form, of course, but with values in tensor square of E. Yes. That's what I want. So I just do it using two expansions. So eta 1 is some expansion like this. Maybe I need to take different order. So omega I tensor S I, right? So this is an element. This is a K form. This is a section of E, right? So, and eta 2, say, is some omega J prime tensor S J prime. So here sum over I, sum over J. Then I define eta 1, eta 2 as follows. It is a sum of omega I wedge omega J prime tensor S I tensor S J prime. The sum over I and J. So this is my definition. Okay. Now this being said, I would like to take my F rho and consider the wedge of F rho with itself k times. Well, I just apply this recursively, this definition, right? And this will make some 2k form for me, right? So this guy lives inside gamma of lambda 2k t star x tensor. So I should take actually this to the tensor k-fold tensor product of this, right? But actually it will live inside. It will be symmetric tensor. It's, I mean, I'm just, let me just tell it to you, and you know, It's just a direct check. Symmetric because this is kind of symmetric in F rows, right? Well, but okay, you can check. So this will be actually Sk of what's written over there, P times M n over add row. And finally, so my final goal is to have a section just of this, right? So I would like to take sections of this and make just functions out of them, functions on X, right? So I would like to take this to C actually. Then out of this I can create some really 2K form on X with nothing, with really values in C.
Ну, F, можете повторить, в каком смысле? То есть вот F вот эта формула,
Да.
форма, она как бы имеет значение в MN, да?
Ну, в том, да. Ну как, в том смысле, что у меня SK V это под пространство в ТК V, где это тензорные как бы тензоры степени К.
Ну, нет, ну это как бы форма.
Ну, это симметричный тензор. Да, нет. Это формой, но у нее есть вторая компонента. То есть форма со значениями где? Вот здесь. Ну, да. Вот я говорю про значение здесь. Что я вот взял столько-то мэйджей, ну, К раз. Вот, это значит, что роль моего И играет здесь вот это. Значит, это векторное расслоение над X. Вот. Значит, я должен его взять, вообще-то я должен написать здесь тензор К.
Да.
Вот. Но я утверждаю, что так как из-за того, что у меня такое выражение, на самом деле там все коэффициенты будут симметричные тензоры. Но можно проверить для К равняется 2, например, если хотите. Вот. Ну просто реально, потому что здесь все f-ки, это один и тот же объект здесь. Вот. Поэтому, грубо говоря, у вас штриха здесь не будет, то они все будут симметричны. Вот. Окей. Then, yes, so now I never used my map F, remember, from Mn to C. So now I'm going to use this map, and well, first I would like to consider Taylor series of it. So let me take some matrix from any matrix from here and multiply it by T, right? And decompose this as, consider Taylor series of this with respect to T. So this will be something like F0 of A plus T times F1 of A plus T squared over 2 F2 of A, and so on. So, yeah, really, notation is that corresponding term is T to the power K over K factorial Fk of A. So this is definition, so this is like a generic term here. So this is definition of, for each K, this is definition of Fk. The function that goes from here to here, and moreover, this function was add invariant, so therefore each f case will be add invariant as well. And moreover, they are of degree k. So if I multiply, if I take fk, multiply t by ta, this is the same as t to the power k fk of a. So these are maps. These are add invariant maps of degree k, each fk. Right. So I would like to now to consider out each of this fk. I would like to construct a map that I will also denote as fk. So this will be from sections of this guy sk p mn edro to to c infinity of x sections of trivial line bundle with anyways to c infinity of x. So how do I construct the fk that goes from here to here? So I need to somehow to make this to map this to c. So anyway, the idea is that if I have some function, like multivariate function, which is symmetric in its entries, then it's actually defined by only by diagonal values. And we just take corresponding fk, look at them, look at this as diagonal values of this, right? And this will give us this map. So namely, what I'm saying is the following. Okay, so let me just start with k equals, I don't know, 1. So if k equals 1, right? So I have a section in here, right? Say s of x is, and for this section, s of x is maybe something like p a. Well, let me fix point x, fix section, and value of this section at x is this. Then I just define my f1 of this section. Gives me something from c infinity of x. Well, this is just f1 of a. So a lives inside mn, right? And fk knows how to eat n by n matrices. So it gives me just, so fn of a, well, this depends on x, right? So this gives me some, so this from section gives me some map on x. Okay, well, I need to choose to check that it's well defined. Well, it's well defined because this is added invariant. For k equals 2, I will just tell you what happens for k equals 2, and you understand how to do it for any k. Okay, for k equals 2, so suppose that I have some polynomial which is symmetric, right? Symmetric polynomial on mn. So, namely, suppose that I have p, which is from S2 of mn star. Okay, it's just symmetric polynomial of degree 2 on mn. Then I can write the following. I can write p of a plus b, so it has 2 entries because of S2. Well, this is just p of, okay, we need to do kindergarten arithmetics, right? 2PAB plus P of B. And so therefore, P of AB is 1/2 of P of A plus B minus P of AA minus P of BB. So if I have something symmetric, then its values are just defined by values on diagonals. So that's what I mean. Okay, then this. So I have this expression.
Что хочется вычислить для...
Да, мы хотим, значит, вычислить, как, значит, для k равняется 2, как вот f2, который имеет есть матрицы, мы хотим понять, как построить f2, который умеет есть, ну, который умеет действовать на симметрических тензорах степени 2 вот от этого. Вот. Значит, вот, значит, рецепт такой, что пусть у меня есть S, ну вот, пусть у меня k равняется 2, да, и соответствующее, and we have corresponding section in here. So I can write its value as, well, it's a, so I can, well, I can assume that it is just a product of two, right? Because otherwise it can just act by linearity. So it is just a product of two things, PA and actually PB. P is the same in here because it's just, I take P the same thing in the fiber of X here. And this is multiplication in the symmetric tensors. So really it's just a symmetric thing. Then I define F2 of S at X as follows. It's just, yeah, I look in here and I define it's 1/2 of F2, this F2, right, of A plus B minus F2 of A minus F2 of B. And then for other cases, just do always the same thing. For k equals 3, right, well, you write P of ABC, right, it will be 1/6 actually, 1/3 factorial of P of A plus B plus C, A plus B plus C, and then some correction terms.
Ну, это направление как бы линейной формулы по квадратичной. Но это в случае двойки, а это как бы...
Ну да. Okay, so now we know how our map gives us a way to map these sections to these sections. And so we actually almost done, because then I define, right, so I take my, so I define the following form, Fk of rho F. I denote it like this. This is by definition. So I apply identity tensor Fk. So this Fk. So I apply Fk to this component of this wedge, like k-fold wedge of f rows. This will be what? One form on, sorry, why one form? 2k form on X without any junk in values, right? It's just values in C. Very well. And so this is now we can formulate statement. Statement is like that. So first of all, this form is closed, and so therefore it defines an element in cohomology. And second, this element does not depend on the connection. So proposition, first, f k of row f, it's in a kernel of D. And second, fk of row f minus fk of row f prime. So this is f. So this is f constructed using another connection, one omega prime, is inside the image of D. Okay, so let's prove this. Okay, so right, for the first part, let me consider trivialization. So psi pi inverse of u to u times g. So this is some trivialization of g, of p, sorry. And then let me choose any basis. Let me denote it as vi of Mn. So Mn is a complex vector space, so I choose some complex basis. Okay. Then what I would like to consider basis of sections of basis in here. So for each vi, I construct a section in here as follows. Right, so it's x goes to psi inverse of x e g vi, and then this gives me a pair, and I consider equivalence class of this pair. So this is local. So for each I that goes from 1 to n square, actually because the dimension of this is n square, is local basis of gamma of s, not s, but just p m, just k for k equals 1, add-row. And again, so you need to, of course, to check well-definedness, because that in equivalence class it gives the same thing, but just basically right? If you multiply by something in here, just this element appears in here, D. Okay, so, right. So this is local basis, and with respect to this local basis, we can actually, it is, so what do I erase? Let me erase here. So it makes sense to write something like this, df rho. Right, so so f rho, let us recall, I think I erased it already, right? So f rho is a section in lambda t star, well, it's two form, so lambda 2 t star x, well, tensor this. So I chose a trivialization of this guy, and so once I chose trivialization, so if I have, so actually if I have any vector bundle here, not trivial, then it's not so clear what D means. You rather need to choose connection, right? So, but when I have in a trivial bundle, I just take D component wise. Right, so I have basis of sections, and in this basis, each coefficient is really a function, right? So I take D with respect to corresponding function. That's it, right? So df makes sense. So and then I claim that, so what I need to see that this is in kernel, so D kills it, right? I claim that if I take differential of fk of rho f, it is the same as, well, ID tensor fk applied to, so fk is this guy, right? But I take differential, and then it will be the ID tensor of k of the following: df rho, which f rho, plus f rho, which df rho, which blah blah blah, plus, and so on. So this is just Leibniz rule. Leibniz rule composed with a thing that fk is multilinear in coefficients of vi. So that's how it was constructed. Each vi is a matrix, right? And this is multilinear in this entries. So therefore, if I apply differential, then Leibniz rule works. Okay. Well, I admit that all of this is a little bit of hand waving, and if I try to check it like very accurately, I will need more than one lecture for sure. So just admit the fact that I cannot avoid hand waving. Awesome. So this is just a Leibniz rule that should be checked, of course, but that's how it is. Okay. Now, now I just want to see that df rho is 0. Then each term is here is just 0. So df rho is 0. It's actually some kind of Bianchi identity. So I take curvature and apply differential one at a time. So triple differential is actually 0. Triple nabla is actually 0. That's kind of what essentially what is going on here. So if you just, well, you need to like more accuracy in triple number, but you kind of need to evaluate it at horizontal lifts, like at 3 horizontal lifts, then it is 0. Anyway, so we can just check it. So I claim that df rho is 0. So df rho is 3 vectors. So it's enough to check df of v, w, and z equals 0 for v, w, and 0 that commute. Well, at each point I can choose like a, I don't know, basis of vector fields that commute. So let me stick with such v, w, and z. But then df rho at v, w, z. Well, there's this formula. Well, we had it for 2 v and w, for one form f. Now, well, it has a generalization to any form. So basically, it says that I need to compute v of f v w minus w applied to f rho everywhere. And this is action on like component-wise action of v, as this is a like vector function, right? In this basis of sections that I chose, right? And here w v z, and then plus f rho. I need to apply z to f rho of v w. So generally, I would also have 3 more terms that would correspond to commutator of different commutators of VW. So I take in the first entry some commutator, and the second what is left, right? But for commuting, this is how it goes. Now, then I claim that v of f rho of wz at x, well, it is some section, right, that like of the same kind as f rho, right? And again, I need a class given by a pair. P is inside ex, and then d rho of omega, and then I need. Let me write first, and then wave my hands to convince you that this is exactly the case. So then commutator of VH with commutator of WH and ZH. And then I need to open close a lot of brackets. So 1, 2, 3. So 2, 3, and then also this one. Anyways, so why this is true? So you take differential of this guy in the direction of V. So this is actually, like, again, so let me, again, I'm using hand waving, otherwise I don't know the better way is rather than go to coordinates, which would be disastrous. So we take differential we take derivative of this function, right, in the direction V. Basically, once you fix P, this means that you take this commutator right, which comes out of this. Consider its coefficients in these sections, right? Well, rather in VI's. These coefficients in VI's, they will give you some functions that we need to differentiate in the direction of V. So this is exactly what VH, when it commutes, it takes these coefficients and act on them and take derivative in direction of V. What is non-trivial here is why is in the commutator I have the other direction when this is composed with this. So VH, ZH, and then VH here. So if VH is here, it just takes derivative of coefficients of this, and that is exactly what we need in here. If we but in the commutator we also have this, right? When this takes derivative of coefficient of this guy, but then this leaves us with VH. But omega kills horizontal stuff, so this will not play the role. Okay. So, anyways. Once again, when I take derivative of this in direction of V, I take coefficients of this and take this derivative, and this happens when I consider this commutator when V is on the left, so it hits the coefficients of this. But the other order in the commutator does not give any thing here because omega kills VH, and that's it. Okay. Anyways, so I have this, and so therefore, I don't know. You're welcome to ask questions, or I don't know. Is it believable what I say? So otherwise, I can advise you to try to do it in coordinates.
По сути, по определению производных.
Ну, надо посмотреть реально, чего там производная от чего берется. Вот я говорю, что берется, реально от чего вы берете производную, это от коэффициентов вот этой штуки. Вот, она там как бы, у вас чего? Вот это FRO, это вот это все, да, без вот этого коммутатора.
Да.
Вот, вы берете просто производную от этой штуки реально.
Почему она внутри, не снаружи?
Вот. Ну, вопрос, почему я могу коммутатор взять? Как бы я в H применяю к коммутатору, да? Но там еще другое слагаемое в коммутаторе, где наоборот вот это применяется к этой штуке.
Почему его нет?
Вот почему его нету? А потому что то, что остается, будет горизонтально, а омега его убивает. Вот и все, что я сказал.
Хорошо.
Вот. Хорошо. Значит, ну а дальше как бы просто тожество Якоби сработает. Значит, I don't know. Let me not write it. So I have 1, 2. So 1. Ну да, вот прям берете, вот это подставляете в каждый слагаемый. Вот. Реально у вас вылезет вот это все от тожества Якоби. И все, это 0. То есть реально у вас как бы... В чем основная движущая сила? В том, что у вас кривизна – это коммутатор. Когда вы берете еще раз коммутатор, у вас вылезает что-то типа тожества Якоби. Вот. Значит, 1 плюс 2, 1 plus 2 plus Jacobi identity gives 1 in part 1 of proposition. Okay, part 2. Part 2 is just, so suppose that omega prime is another principal connection. And well, if you just consider the difference of omega prime minus omega, then you can form omega t, which is just form depending on parameter, which is basically just a straight path from omega to omega prime. So it's omega plus t eta. And you can check that if omega prime is principal connection, omega is principal connection, and omega t is also principal connection for each t. Basically, this is just because we saw this when we started doing connections, is that connections are affine space. Right, so meaning that any straight line, if you go along any straight line, you inside you going over connections. We saw something like this when we introduced affine connections. Okay, okay, so these are connection also principal connection. On P. By the way, you just can take this definition using omega and check this qualities. So this would just mean that eta will satisfy the same condition for et and alpha g, and also eta of psi bar is 0. Because this is of psi bar is psi, this is psi bar is psi, and so therefore these two conditions they work for any. So what you need is that eta of psi bar is 0. And so these two conditions they work for any t. And so you check that this is really principal connection for any t. Okay. Well, I can also define some stupid projection. So this is just, I don't know, pi is not so good. Well, okay, I don't have pi anywhere else. So this is just projection on the second component. I can consider pi star p. This is also principal G bundle. And but over this already. And omega, so I can consider omega tilde connection on pi star p given by, so this should be defined for each point in here, right, which is t, which lives in the interval, and x, which is an element in the manifold x, and this is just by definition omega t of x. And again, this is also principal connection, but on pullback, so which lives in here. And so, right, the main idea is that first, your space of connections is actually affine space, so to say. And second, we just use the first part of the proposition. So this gives connection pi star p, so we can form f tilde, which is like curvature 2 form. And so this is curvature corresponding to this. Also, we can form ft, right? From omega t, we can corresponding curvature is ft. And then f tilde is just can be written like this: dt wedge some eta, some form, plus ft. Well, it just, again, this is as going through definitions. You can see that this is actually given by f tilde is given in such form for some eta, some form eta. And then f k of rho f tilde, so this is our form that we constructed, is actually dt wedge some form eta k plus fk of rho ft. Again, going, like if you look closely to definitions, which takes some time, you cannot go like that, then your fk is just has something with dt inside, this form, plus everything else without dt. And this everything else without dt is exactly the form that we defined for this curvature. Okay, but then dfk of rho f tilde is 0 according to part 1, right? And this means that partial derivative of fk with respect to t of rho ft, so this thing, equals to d eta k. Right, so compute differential of this and take its coefficient for dt. So then you'll get this. Right, and so then I just take and compute, integrate the last equation, right? So integrate, I'll get value of this at 1 minus value of this at 0. Value of this at 1 is exactly fk of rho of f. F prime, I think, right? At 1, it is f omega prime, so f prime, right? So I just integrate, I'll get fk of rho of f prime minus fk of rho of f equals to integral from 0 to 1 of eta k. Well, differential commutes with integral with respect to t of like this. And this is exactly what we wanted. So this is exact. So this is exact form. So therefore, really, it defines a class for us, which we will denote. So fk rho f, right, defines class, homology class, which, well, I will write it like this. So it doesn't depend on f, but rather depend on rho, f, and p, principal bundle. And so it is a class. And it is an element of h, 2k, the RAM of x.
То есть идея в том, что мы связность определяем с помощью какой-то, омеги, которую мы придумали, определили ее.
Не связанность, в смысле, а вот эту форму?
Нет, я дальше хотел сказать, что условно, как бы мы ни взяли связность, мы можем ее по-разному брать, но fk
Да.
у нас в итоге будут отличаться только на экзакт форме.
Да. И поэтому у нас кримология это одна и та же. Вот. Ну все, круто. Значит, осталось чего доказать? Доказать, что когда у меня P изоморфны, то значит, класс характеристически один и тот же. Вот. Но это быстро делается. Okay, so we need to prove that it is actually characteristic class. Again, it is not hard to say once you thought about this for some time. Again, you need to go through definitions, and while you look at them closely, you get the following proposition. So if my P is isomorphic to some other P prime, both are principal bundles on X, G principal bundles, then Fk of rho P, this class is just equal to Fk of rho P prime. Well, so proof, if you have isomorphism corresponding phi, you can take connection on P prime, denoted omega prime, and you can pull back it. This will give you connection on P. Again, I am saying all this, but of course one should be accurate. So this should be also principal connection, and you need to check the conditions that we had today. Ну, это из-за того, что изоморфизм, да, ну, вам нужно понять, что действительно у вас как бы все эти свойства омеги сохраняются, что он там кси-бар в кси отправляет, и что как бы я пулбэчу относительно альфа-G, я получаю присоединенное действие. Вот. Окей. This is one thing, so let me denote it by omega. And the other thing is that, again, since my connection on P is defined from connection of omega prime, my horizontal lifts are related accordingly. So actually my V H bar, which is horizontal lift to P prime, according to this connection omega bar, is actually phi, like push forward of phi star of VH, which is horizontal lift to P. Just because my connections are related like this. And then, well, then I just take, the whole construction was built on the following expression. At some point P prime, right? So P prime is, so here P prime is phi of P for some P. So I need to, so how to, does this expresses in terms of things without primes. So then I have that it is pullback. Then just definition of pullback. This is phi star of omega prime of phi, well, at point P prime, right? This is the same as phi star of omega prime of phi lower star inverse of VH prime, phi star lower star inverse of WH prime at point P. This is just definition of pullback. It works like this, and then it is really what we get. So this is just, this gives me just VH, this is WH, right? And pull back gives me omega. So this is just omega of VH WH at P. So this thing that sits as a building block for our construction is just invariant with respect to isomorphism. And that actually proves everything. It was hard part to prove that it doesn't really depend on connection, and then you can take whatever connection is convenient for you. In this case, it's just a pullback connection, and everything follows. Okay. Okay, so we are out of time, but let me say some words because, well, those of you who know about Chern classes and maybe some other, so there are now particular examples of our construction. And usually, actually, people define all these classes not using curvatures, but rather some other constructions that I don't have time to talk through, but to go through. But at least let me see how it, spell out some names that for some particular cases. So suppose that I have E, which is a vector bundle, and it is complex. So over X, so complex vector bundle. Then I actually can consider P GLE. So this is GLNC bundle. Complex rank N vector bundle. Then I can take my F to be the following thing. Well, first I need to take rho, and rho is just a tautological representation. We just sense GLNC to GLNC, right? So GLNC acts on Cn in this representation. So this is just identity. And then I need a map from all n by n complex matrices, right, which is invariant. Well, this map is just f of A is just determinant of identity plus, just to match all definitions and other sources, you need some coefficient here times A. So take F to be like this, and then what you have is that Fk of rho PGLE is called the kth Chern class. And very useful exercise or proposition. So with what we covered so far, so I thought we will have time for that, but since not, let me just formulate. So if my E is just a direct sum of line bundles, so rank, complex rank of each EI is just 1. Maybe it's just proposition. Then, well, let me denote this as Ck of E. And yes. So also I can compute, so I can take sum of all k from 0 to infinity, but actually this will be some finite thing of ck of e. So this is called total Chern class. And so if E is a direct sum of line bundles, then C of E is actually C plus 1 plus C1 of E1, 1 plus C1 of E2, and so on. 1 plus C1 of En. In other words, your Ck of E is elementary symmetric polynomial, which is usually denoted like this, in C1s of Eis. So it's a good, I think, way to understand everything that happened today is try to prove this by yourself. So actually this can be proved just from what we now. So it would be easy that if all vector bundles would be direct sums of line bundles, but this is not it. And actually, Chern classes are defined like from this side and using so-called splitting principle. Splitting principle says that if I have a vector bundle of rank R, or N, I don't know. So this is rank R, okay, N. And then there exists some smooth map, I don't know, let's call it phi, from Y to X, such that pullback of E is sum of line bundles. So this is called splitting principle. And here it's actually like this. Yes, and so usually you first start with defining C1 of line bundle, and then using splitting principle define Chern classes as inverse images of the pullbacks of symmetric functions of C1s of E. Like this is, but this takes more time, and basically in our construction all classes already kind of there. Yeah. Another neat result about principal bundles is that they actually classified as a pullback. So all bundles, all principal bundles over some fixed X, they are classified by some classification space. I don't know. Usually they are classified by homotopy equivalence of pullbacks from X to some fixed BG and some fixed bundle PBG. So this is like a classifying space for all G bundles over X. So basically all principal bundles, they appear as a pullbacks of some classification space. And this is very cool. For example, all vector bundles, they appear as pullbacks of tautological bundle over Grassmannian. And so well, if you know the map, like this, with respect to what you pull back. To compute characteristic class, you just need characteristic class of tautological bundle of Grassmannian, for example. So not, yeah, but this happens for any G bundle. You have this crucifying space. Okay, so I guess we'll stop at this point.